All right, so we just saw how the disk method gave rise to the washer method and how that was used. We did that with example 4. In this video, we're going to keep going and we're going to look at the other examples in this section and take a look at those. So what I'd like you to do is try example 5 on your own. Read and do that problem. Now, I am going to do this problem right now. If you haven't done this yet, which you probably haven't because I'll only give you a few seconds, please push pause on the video that you're watching and go ahead and do it on your own and then come back to the video. Okay, so the first thing that we're going to do is I'm going to draw the region that we're looking at. So you can see the middle two graphs are just the middle two curves are the x-axis, y equals 0, and the y-axis, x equals 0. You can see x equals 3. We know what that is too. That's a vertical line at x equals 3. And then 3 over 1 plus x, that's probably the curve that's most difficult to draw because that's obviously a rational function. But if you take a look at that rational function, again, this is the y-axis, which again, graphed as x equals 0, x equals 3. Oops. The rational function does this. And if you note what points this goes through the point 0, 3. And this down here obviously is the point 3, 3/4, right? I believe. Okay, this obviously is 3, 0. And you can see that this little region here is the bounded region that we're dealing with. I'm going to erase some of the lines just so it gets a little bit less messy that stick out of there. So we're looking at that region. Okay? Now, what line are we rotating it around? We're rotating this region around the line y equals 4. That's up here. So if you want to, you can erase some of this, make it maybe easier to see. We're rotating around the line y equals 4. So we're going to get a ghost image that's up here somewhere. Okay? A little bit there. Again, ghost image is not an official term, but I use that term a lot. Okay, so as we do this, the rectangle that we're going to draw, the one that I really want is this one. The one I've shaded in green. I want that piece to be rotating around and calculate that value. The way I get this rectangle is by doing the big minus this empty value, right? In other words, we're using that washer method again. And so the larger of the rectangles minus the interior that's empty. Okay. This almost, by the way, looks like a tube. It's a little bit of a weird shape to the inside, that object. So there we go. Let's set this up. When you set this up, the volume, again, is going to be the washer method. But as you can see, the rectangle width-wise is in the direction of x. So we're going to do r of x squared a b integrated from a to b times pi minus that same integration with a smaller radius squared, all with respect to x. Hopefully you can read that. I know that's fairly far over. Okay. All right, so a to b, we're going with respect to x. We're going from 0 over to 3. So from 0 to 3, that's where we're integrating to and from. The larger radius. Now, this is a little bit tricky. It doesn't actually matter because we're squaring things, but technically speaking, the larger of these two radiuses is going from y equals 4 down to y equals 0. So the larger radius is going to go from 4 to 0, and then you're going to square that. By the way, if you think about the radius and you say, well, I was thinking actually it should have gone from 0 to 4 because that's the outside part to the inside part, you're going to get the same answer in the end because of this squared component. So if you went 0 minus 4 and then squared it, you're going to get the exact same thing as 4 minus 0 and then squaring it. All right. So it's not that big of a deal, but if you actually want a positive radius, you go 4 minus 0. All right, that's the outside. The inside goes from 4 down to this curve. So from y equals 4 to y equals 3 over 1 plus x. So you would write 4 minus 3 over 1 plus x squared dx. It takes a second to type that into your calculator, but again, it's nothing over the top. I'm typing it in now. I guess you can see me type it in. Let me put that up. I left off the 0. It's not that important. So I think I got all my parentheses in there correctly. If I type in enter, I get about 83.32. Write that down. If you divide this one by pi, you don't get a nice answer. So you don't get a whole number or a nice fraction that you can convert. It just does not work out, right? You can't convert that into a fraction. And so it doesn't come out to be a nice fraction because of that 3 over 1 plus x, when you're integrating with that, you end up with natural logs. So that's fine. So we're just going to call this about 83.32 and then call that a day. Right? Call that. That's the finish of the problem. All right. Again, if you need help, pause the video, roll that back, and go over that again. Sometimes I go fast, sometimes I go slow. Slow for some people, fast for some people. So you can always go back and rewatch that. Okay. So I'd like you to do example 6 on your own as well. So push pause on the video, and I'll give you about 5 seconds, and then I'll start doing this. But push pause on the video and do it on your own. Okay, so I'm going to start doing this problem. The region that we're going to create is is bounded by y equals 5 minus x, y equals 0, y equals 4, and x equals 0. And we're going to rotate around the line x equals 5. So the first thing I need to do is draw this region and figure out what it looks like. Okay? Y equals 5 minus x. Y equals 0. Y equals 0 is the x-axis. X equals 0 is the y-axis. 5 minus x is a line that does that. Y equals 4. Y equals 4 is a horizontal line that does that. Now, you'll notice that this created 2 bounded regions. The 2 bounded regions that we created, we have a triangle and this quadrilateral. It turns out the one I need is the quadrilateral. The reason I'm going to use the quadrilateral is that's the one whose perimeter carries each of these components. If you use the triangle, obviously the line y equals 0 is not on the perimeter of that triangle. So the only bounded region that's bounded by these 4 curves is this one, the quadrilateral. We need all 4 to be bounding there. So I'm going to erase a little bit of this stuff and draw some points. All right. The origin, that's one of our points of our quadrilateral bounds. Over here, this is the point 5, 0. This is the point 0, 4. This is the point 1, 4. So our quadrilateral has those at the intersections. Those points as the intersections. We want to rotate around the line x equals 5. Now I have to undo this because I kind of screwed that up. Because x equals 5 is a vertical line, and it turns out it goes right through this point here. Right through 5, 0. okay? So we're going to be rotating around x equals 5. Now, if we're rotating around this vertical line, that means my rectangles that I draw are all going to be laid out horizontally. And notice that the region, when I rotate it around, we're going to have an open space in the middle. So the rectangle that I really want is this one that I'll try to fill in. Might be hard to see because that rectangle is so thin. But make that a little thicker, I guess. Maybe that's easier to see. Maybe it's easier that way. But we got the filled in part and then the empty part. So we're going to use the washer method, but the washer method with respect to y for obvious reasons. Width of that rectangle is done with respect to y. Now the washer method, when we do it with respect to y, the change is only between using the letter x and the letter y. And then when we deal with our integration, everything has to be done with respect to y. All right. So let's take a look at this. Let's take the larger of the rectangles. Larger of the rectangles. So the large rectangle goes from the line, again, depending on whether I want to make my radius positive or not, whether I start at the right or left, from the line x equals 5 to x equals 0, right? From x equals 5, that's this line here, to x equals 0. That's going to be the radius. Oh, you know what? I should have done one thing first. Let me do the bounds first. I apologize. With respect to y, the bounds go from 0 to 4. So go from 0 to 4. Those rectangles are going to go all the way from y values of 0 to y values of 4. So when we calculate the value, we're going to be integrating from 0 to 4. Now, bigger radius goes from x equals 5 to x equals 0. So we go 5 minus 0 as the big radius. The smaller radius, I ran out of room a little bit. That's okay. Crap. I'll just erase this. The smaller radius goes from x equals 5 to this line here. Now, this line here is the line y equals 5 minus x. We can't say 2y equals. We need to solve this with respect to x. And if you solve this with respect to x, add x to both sides. X plus y equals 5. Then subtract y. You get x equals 5 minus y. So it goes from x equals 5 to x equals 5 minus y. All right, again, we have to solve and solve for x, solve with respect to y, so that we can put it in our formula and integrate with respect to y. So 5 minus 5 minus y. Now, when you type this in, be very careful of this minus sign. This minus sign technically needs to distribute into both pieces. It's not a huge deal on this problem, but on other problems, being able to distribute that minus sign is going to be a big deal. And so just be very careful with the parentheses there. So we could type this in. Let's go ahead and do that. So integrate, well, pi integrate from 0 to 4, 5 minus 0 squared with respect to x. Now, I wrote with respect to x because really that's the only variable my calculator can type in, when in reality we're dealing with y as our variable. So minus pi 0 to 4, 5 minus y. And then all of that needs to be squared. Integrated with respect to y. So I got about 247.14. If I divide by pi, that means about 78 2/3 pi. Okay, so you can call that 78 2/3 pi, or you can call that approximately 247.14. Either way. All right, hopefully that all makes sense. By the way, that's about as hard of a problem as this section has. Okay, we threw a lot of things at it, at this problem. Space in between, integrating with respect to y, having to solve things for y, solve things for x, or solve things with respect to y is what I'll say. All that kind of good stuff. Rotating around a line that wasn't one of the axes. So that's about as difficult of a problem as this section gets. That threw all of the toughest parts at you. So let's go ahead and do another set of problems. Now, here's what we're going to do. In the next 4 problems, I'm going to take a certain region. This way, we don't have to redraw the region every time. We're going to take that region and revolve it around different lines. So the region here is created by the parabola y equals 2x squared, the curve y equals 0, and the curve x equals 2. And first, I want you to revolve this around the x-axis. Go ahead and push pause, try to do this problem, and then in a few seconds, I will do it on my own. Okay, y equals 2x squared, y equals 0, x equals 2. That's the region I'm looking at. That's the bounds on the region I'm looking at. And we want to revolve around the x-axis this time. So let's draw the region first. Y equals 0 is the x-axis. X equals 2, right here. Y equals 2x squared is this. Obviously, here's the y-axis. I really don't need that for this problem, but there we go. So we want the bounded region where these three curves form the perimeter. And that means we're looking at this region here. Okay? So this region right here. I'm going to erase some of this other curve just so we can make it a little bit cleaner. Hopefully we got that. So here we are. By the way, that's the 0.28. The way I figure that out is we know that's on the line x equals 2. When x is equal to 2, y is equal to 8 on that curve, right? So I know that's where it intersects. Here's the origin, 0, 0. Here's the 0.20. Now the first curve I want to rotate this around is the x-axis. Or the line y equals 0. Rotate that around this axis. Well, this is nice. This is a really nice one because when you rotate around the x-axis, we have a solid rectangle. That's the first time in a while we've had a solid rectangle. Okay? Some people will actually even fill in the rectangle to signify that it's the whole thing. Notice that rectangle is done with respect to x. We're rotating around a horizontal line. And then we go, well, this is an x value. So this starts at 0, goes to 2. Integrate from 0 to 2. Well, it's poorly drawn. That's okay. And then the radius goes from top of the rectangle is y equals 2x squared down to the bottom of the rectangle, which is y equals 0, again, the x-axis. So 2x squared minus 0. Make sure you square that whole radius. By the way, that's one of the more common things that I'll see on the test. People will accidentally forget to square the radius. They'll be so caught up in figuring out what the radius is, they'll forget to square. Okay? And then type this in. Now, I'm going to type this in. I won't project this on the overhead this time. But when you type this in, nothing real cumbersome on this one. You get about 80.42. And if you divide by pi to see what the exact answer is, it's 25.6 times pi. That's the exact answer. Okay. Again, pay whichever one the Moodle's asking for or the homework's asking for, write that one down. Usually, again, it's either an exact answer with pi in it or rounded to 2 decimal places. So there you go. Now, I want you to do the another problem. Instead of rotating this region around the x-axis, why don't you go ahead and rotate this region around the y-axis? Again, push pause on the video. Try this on your own. And then in a few seconds, I will do the problem. All right. So I'm going to go through this quickly. We want to rotate around the y-axis. We have this region. Since we've drawn it this way, we want to rotate around a vertical axis. We need to utilize the washer method. The area that I shaded in, that's the area that I want rotated. But in order to do that, we're going to have a big rectangle and with a piece missing. We're going to have a washer. Okay? So I'm going to be integrating with respect to y. By the way, with respect to y, notice this is going to go from 0 to 8 in terms of my y value bounds. So 0 to 8. Let me just write radius with respect to y right now. And so now we can figure out what the radius needs to be, or what the radii, I should say. There's two of them going out here. All right. So take the bigger rectangle. On the bigger rectangle, the end line here is the line x equals 2. The line over here, obviously the y-axis is the line x equals 0. So if you go from right to left, it's from x equals 2 to x equals 0. So the bigger radius is from 2 to 0. Okay. The smaller radius, I should have wrote that. So that's the big. Well, we're rotating around x equals 0, so that's, again, 2x equals 0. That's pretty straightforward. And it goes from this curve down to x equals 0. So it goes from this curve down to x equals 0, but I have to rewrite this curve. So I'm going to divide by 2 and go x has to be the square root of y over 2. Notice I used a positive square root because we're in the first quadrant. So it's from x equals positive square root of y over 2 down to x equals 0. Again, this is one of the more difficult ones because we have to integrate with respect to y. We have to do all that kind of stuff. Integrate with respect to y and have space in between. So that's a difficult one there. But we can still do it. So take square root y over 2 down to 0 squared dy. Type this into your calculator. Again, it's probably not interesting to see me type things in, so I'm just going to do that and say what I got. Oh, shoot. I ended up with about 50.27, which as an exact answer is 16 pi. So I ended up with 16 pi, which is about 50.27. Okay. By the way, notice how difficult that was. That's a fairly difficult problem there to deal with. All right. I want you to try 7C on your own as well. Again, same region. Now we're rotating around the line y equals 8. All right, so let's go through this on our own, or to me, do this together. Hopefully you've done this on your own by now. If not, push pause on the video. So y equals 8 is a horizontal line. I should have used green there. Horizontal line, y equals 8. That means when we're dealing with the rectangles that we're trying to draw, we're going to draw these vertically. And I'm going to have to use a washer method. I'm going to have part of the rectangle, part of the region. I want to rotate, but there's going to be another with a hole in it, right? Now, because the rectangles are drawn this direction, we're going to be integrating with respect to x. So washer method with respect to x is what we're going to use. Okay? All right. Again, I'm trying to speed up a little bit so that this doesn't bore you to death, but bounds, since we're dealing with x values, are going to go from 0 to 2. We'll do that over there too. Bigger of the two rectangles goes, again, depending on whether we want, I usually do top to bottom. That way I get a positive radius. If you go top to bottom, you go from y equals 8 to y equals 0. So from y equals 8 down to the x-axis. So from 8 to 0, that's our bigger radius. The one that we're missing out, our smaller radius, again, when you go to your smaller radius, make sure you're going up to the line you're rotating around, right? So it's from here to the line we're rotating around. If I want to make that a positive number, I'm going to say from y equals 8 down to where it hits this line right there, down to y equals 2x squared. So my smaller radius is 8 minus 2x squared. And then we type that into the calculator. So again, I've done that enough. Hopefully that should be fairly straightforward. What I'm doing here, at least. And I ended up, now I typed it in quickly, so I gotta make sure I got the right number here. I ended up with 187.657 blah, blah, blah. So about 187.66. As an exact answer, we go divide by pi. That's 59 and 11/15 times pi. All right. So that's an interesting number there. All right, so that's 7C, rotating around y equals 8. Now for the last problem I want you to do, I want you to take that same region and rotate it a lot around the line x equals 2. Raise this thing so much. Okay, so I'm going to start here. If you haven't done it, just push pause on the video. Okay, so x equals 2 is the vertical line, is the vertical edge here. And anytime we have the situation where one of the edges of the region is the line we're rotating around, then I always get happy because then we have no space in between. All right. So if we rotate it around here and we draw the rectangle, looks like that. No space in there. Okay. Rotating it around. Notice this rectangle is going to be done, is going to be width with respect to y. So it's going to be a single disk method done with respect to y. Oh, can't hit that. All right. Now, bounds on y, lowest y value we're going to be dealing with is 0. Highest y value we're going to be dealing with is 8. So the bounds on y are going to be from 0 to 8. The radius of this thing, be careful. If I want a positive radius, I have to start at the right-hand side and then go to the left. So I'm going to say from the line x equals 2, that's the right-hand side, to this line here. Now, I already solved for this earlier. That curve written as x equals is x equals y over 2 square rooted, or x equals the square root of y over 2. Again, we always have to do that when we're talking about with respect to y. We always have to go from a function written with respect to y, x equals, to a function written with respect to y, x equals a function with respect to y. So my radius is 2 minus square root y over 2. So we're going to square that number and then integrate from 0 to 8. Okay. Make sure you have parentheses done correctly. Hopefully, I've typed it into my calculator in a good sense. It took a second to actually calculate this because, you know, when you have square roots around 0, it takes your calculator an extra moment to do that. Basically, this one came out on my calculator as about 16.76. All right. One last thing I want to mention is that if I try to get an exact answer by dividing by pi, we see that this is 5.333, and then I got 1, 2, 3 at the end. So it looks like it's supposed to be 5 1/3, but the decimal is off at the end. This is an issue with our calculator because oftentimes the calculator, when we're trying to integrate around 0 with square roots, our calculator is going to end up approximating that. And we should have ended up with 5 1/3 here, but we had almost 5 1/3. So that's important if you're trying to find the exact answer. If you're trying to find the exact answer, you have to realize that your calculator can mess up and instead of doing all the calculations perfectly accurate, it might mess up at the very, very end of that decimal, okay? Again, that's a problem when you're integrating close to asymptotes or close to the start of a square root. All right. So there we are. All right. Hopefully you don't have any questions. We're going to stop there for section 7.2. And we're going to see next time another method for calculating value. Okay? So we're going to look at another method for calculating value. Next time, you might ask, well, why do I need another method? Well, because not all functions are easy to solve for x. Not everything is easy to do using space in between. So this next method we're going to be dealing with is going to deal with those things a little bit nicer. All right? So that's the end of this video. End of section 7.2.